Hey statisticians, now we're going to take a look at making a two-sample t interval for the difference between two means. And just like before, we've got the situation where we are going to have two different populations, and we're going to be drawing samples from each of those populations. In the first population, we'll get some sample mean number 1, and it'll have some sample standard deviation. In the second population, we'll get some sample mean that we'll call it sample mean 2, and it will have some other standard deviation, because this was our first population number 1, this is our population number 2. And now our goal, since we're making an interval, our goal is to take this sample data and only the sample data. We'll know nothing about the population. The population standard deviation is unknown, right? It is not known by us. So we're going to take this information and we're going to try to come up with an estimate. The goal now is to make an estimate for what is the actual difference in the true population means, right? So this population's got some mu1, this population's got some mu2. Our goal is to estimate what is the difference, say, mu1 minus mu2, right? And remember, this is more information than we would just get if we did a significance test. In a significance test, we're just going to be trying to disprove certain hypotheses. Now we're actually going to try to figure out what this actual difference is, how much of a difference really exists between these two things. So we did an example in terms of our test video that we'll just use for make our interval. Remember, here we were looking at paint drying, drying to the touch, and we had these 35 random samples of each type of paint, different painted surfaces, and we found this sample mean, the sample standard deviation. We ended up getting a p-value using, remember how we talked about there was actually 2 degrees of freedoms, and if you didn't see that video, I'll talk about the 2 different degree of freedoms that we might particularly use here, but we ended up getting p-values that were pretty small, 2.9%, 3.24%. The 2.9% is really the most true one, but that would probably, say, at a 5% level of significance, cause us to reject the null hypothesis and say that there really is some type of difference in the population means here, like the difference is not equal to 0. So if I want to do a confidence interval would actually give me an estimate for this, right? So let's look at this scenario, right? So if I wanted to come up with an estimate, remember that a confidence interval always begins with a point estimate. In this case, our point estimate would be what's the actual difference between the two means that we have. The difference in our sample means is our best guess for what the difference is going to be in the population means. And of course, we're going to add to that some kind of margin of error. And this margin of error is going to start with some type of t statistic, and this is going to be some critical t value. So I'll put a little star next to it in some way to say, like, hey, there, I'm extra special. This t is going to be really important. Of course, what t we use is going to be based on some particular degree of freedom, and we'll explore the degree of freedom again in just a second. And then this critical value gets multiplied by some standard error, right? In this case, it's definitely a standard error because it's going to, I don't know sigma, and I'm going to base this formula on sample values. So just like we saw before, we'll have a big square root, and we'll take the standard deviation of our first sample and square it over the first sample size plus the sample standard deviation of our second sample, square that over n2. And of course, this was all based on the standard error formula, right? The standard error formula that we knew in the past. We had to take the standard error of the sample mean, we had to square it to turn into a variance, and we end up getting s squared over n, and that's what we're adding together here. Remember, do you ever add standard deviations? No, you always add variances. So very good. If I was to carry this out, that would be cool. I could just plug in values for this particular scenario here. Remember, we knew this first sample, the amount of time it took on average for the paint to dry was 68.1, and the second was 63.7. If I calculated the difference there, then that comes out to being, I calculated this before, it came out to being like 4.4. Let me do it again. 68.1 minus 63.7. Yeah, it was 4.4. So this, my first best guess, my point estimate would be 4.4 plus or minus. Now I need a particular t. And of course, this t is going to be based on a degree of freedom. We saw in our other video that the degree of freedom actually comes in 2 ways. And lots of craziness. If you haven't watched that video, you'll see where all this craziness came from. But there was 2 approaches. There was the conservative approach, which would mean if you don't have any fancy calculator that could do some crazy formulas for you, then you could just simply take the smaller of the 2 samples sizes, n1 minus 1 or n2 minus 2, and say the degree of freedom, just like we saw in one sample t procedures, is just the sample size minus 1. So you pick whichever one was the smaller of these. In this case, since both of the sample sizes were 35, we would just do a degree of freedom of 34. And then you could either go into your If you had a table, you could look up for degree of freedom of 34, but actually the table doesn't even tell you that. So the other way to get it is if you had inverse t. Now, some of you with older calculators, you don't really have an inverse t thing going on here, right? So for our test statistic, it's based on a degree of freedom and then say a level of significance. So let's say we did, or excuse me, a level of confidence. Let's say I wanted to do an interval with 95% confidence, right? Then my tails on the end for 95% confidence would both be 2.5%, right? So that I would have 95% in the center here, right? And so if I was to use inverse t, I could do something like, let's make the area 0.975. That would be 2.5% plus 95%. So as everything to the left, remember inverse t requires you enter in like a percentile area, a less than area, everything to the left. And so if we use a conservative degree of freedom, I could just hit 34 with that, and then it would say my test statistic is, excuse me, not my test statistic, excuse me, not my test statistic, my critical t, test statistic is for a test. My critical t would be 2.0322, right? So one option is I could use, if I use the conservative approach, I would have 2.0322, and then of course I could plug in my standard deviation stuff, right? So I'll write those real quick. In this scenario, the first sample had a standard deviation of 8.4, the second sample had a standard deviation of 8.1. So if I was to fill this in, it would be 8.4 squared over 35 plus 8.1 squared over 35. And that won't change. So that's what my critical t would be if I use the conservative approach. Now, if I want the true degree of freedom, then it's actually calculated by statisticians. So they came up with this really beautiful formula for coming up with a degree of freedom that, again, relates to the amount of variability in each of the samples and the sample sizes and all that. Ends up coming with a degree of freedom that actually usually comes out to a decimal. Now, if you want to know what that degree of freedom would be, you might as well just, you're not going to sit there and plug all your numbers in the calculator on the test. Like, this is what was going on here. In reality, you don't need to know this formula. I've only a couple times had students actually plug values into this formula to figure out the degree of freedom just because they were extra special kids. They thought stuff like that was fun, so they did it. But the calculator really completely does it for you. If you go to stat and you go to tests and you do a 2-sample t interval, because now we're doing intervals, a 2-sample t interval right there, right? Oops. 2-sample, I lost it. 2-sample t interval, for me, it's option 0. You click on that, and then you just plug in all your data. I got 68.1, 8.4, 35, 63.7, 8.1, 35. Confidence level is, say, 95%. Hey, do we want to pool here? Do you guys remember if you watched the other video? Answer, no, we never want to pool. If you're trying to calculate a p-value, don't pee in my pool. The only time and I'll talk about what pooling means actually at the end of this video. But let's say no for pooling, hit calculate and Shazam. We have this confidence interval. So this 95% confidence interval suggests that the actual difference, right, would be, I'm going to write this down. This is the best confidence interval, 0.46394 up to 8.3361 minutes. And this is in minutes. That's the minutes dry time. But let's check here. What was the degree of freedom that this guy used? Notice it's right there, 67.9. About 67.91 is the degree of freedom, right? And so that will end up giving us a critical value that's larger or smaller. It actually will give us a slightly smaller critical value than the one we had here, and we can check. So that the actual degree of freedom that the calculator uses was 67.91. And now if I want to check what that critical value was, the calculator doesn't tell you there. You could, again, go to inverse t if you're just curious. And instead of the degree of freedom of 34, we could put in 67.91. And hit paste and see the critical value that the calculator used was 1.8216, right? Ooh, wait, that's not right. I did X times. I was like, that's not even make any sense. I apologize. I somehow had a stray X that got stuck in there. I don't know where my finger was slipping. No. The critical T that the calculator used was, that makes much more sense. 1.9955, right? So the calculator ended up using a critical t of 1.9955 instead of this when the degree of freedom was 34. That's the better and that's the better guide, because in general we want our confidence intervals to be as narrow as possible. So if we can have a higher degree of freedom than we estimated with the conservative approach, then we should go ahead and do that, right? And that gives us a narrower interval than we would get otherwise. Just as a side note, notice this 1.9955 is really, really close to some special number. We've been talking about 95% confidence for a long time. What's the critical value for 95% confidence if it's with a normal distribution? What is it? Oh, did you say 1.96? Yes! So if this was a normal distribution, then the z would have been 1.96. Notice that we're starting to get something that's much closer to 1.96 because that the t distribution approaches the normal distribution as the degree of freedom goes to infinity. So that's kind of nice. So okay, let's take the calculator gives us the best confidence interval. In this case, this confidence interval gives me much more information than simply whether I could reject or fail to reject the null hypothesis. If we had a significance test and the null hypothesis was that the difference was 0, we do have evidence that the difference isn't 0 because 0 is not in this interval. But notice how much of a difference really can we say there is between these two types of paints? Not necessarily a whole lot. This is actually still a pretty wide interval for us. We're saying that it might be as small as like a half a minute up to about 8.3 minutes is the difference between the averages here. So if we really, really, really want to know how much of a difference there is between these two paints, we'd probably just want to take a bigger sample size. And a larger sample size might reveal more to us about what's going on here. But okay, so that's how we could do a two-sample t interval. The conservative approach would say get your critical value for your level of confidence from just doing the degree of freedom, the smaller degree of freedom from either your first sample or your second sample, which of course don't always have to have the same sample size. But the better approach is just done entirely in the calculator. There is a pretty wild formula that involves standard deviations and sample sizes, but you don't have to have that memorized. You can just put it in your calculator and go for it. Now, I promised at the end of this video I would say something kind of interesting about pooling, and actually that's related to this degree of freedom formula. So here's a fun fact. Now this is not for AP Stat, so if you only want to know what you need to know for AP Stat, you can just turn your ears off now or shut the video off and don't watch. No, please watch. It's really great. But what would be the degree of freedom? What's the degree of freedom if we pool? If we did a pooling, right? And really pooling, what the pooling would do in our procedure, it really changes the degree of freedom for that critical value. And so what does pooling even mean? Well, actually, if you recall, let's take a step back. When we were doing a two-sample, the two-sample z-test for p, we actually did pool there. Remember how when we were trying to come up with an estimate for p, we actually combined our two samples together, n1 plus n2 and x1 plus x2 as a numerator, and this was our best estimate for p. Well, remember we did that. Why did we do that? Because we had a null hypothesis that p1 was equal to p2, and because we assumed that they're equal, we could combine our samples from population 1 and population 2 to get things going here. So what is that? How does that relate to here? Well, when we're talking about a mean, the pooling is an assumption that the standard deviation from your first population is actually going to be equal to the standard deviation of your second. And so if the standard deviation of the first population, standard deviation of the second, the standard deviation of your first population is equal to the population standard deviation of your second population, then some cool things happen with the degree of freedom. This crazy formula. And actually, I can leave this as an algebra exercise for you. If we assume that sigma 1 and sigma 2 are known and are equal, then you can well, maybe not that they don't have to be known, but if they're equal, if you just say that the sigma, substitute in here just a sigma squared and do a bunch of math, then what ends up happening is this degree of freedom goes way down. The degree of freedom ends up becoming your first sample size plus your second sample size minus 2. In other words, you just end up adding the separate degrees of freedom from your two sample, right? If you did n1 minus 1 plus n2 minus 1, you'd end up getting, boom, right, n1 plus n2 minus 2. Now, if you want to do a bunch of algebra, you can try to show that if you just take out the S1s and the S2s and replace them with a single sigma, and you do a bunch of math, and you can just see how the magic happens, and it's pretty glorious. And so, of course, that's based on that assumption. In AP Stat, we never make this assumption, right? This is never something that we assume, so we'll never use use this formula. Again, you can see how the algebra works out, but it's kind of cool. In this particular instance, it might not be a terrible assumption though. If you notice that our two sample standard deviations were pretty close, and so it might not be unreasonable to assume that the population standard deviations were actually equal, but we're never ever gonna make that assumption in AP Stat. So ignore, if you just want to be able to do well on a test, ignore all this stuff. This is just a fun fact to make your life more enriched. So anyway, guys, hope this was helpful. Here we learned to do a two sample t-interval to estimate the difference between two population means. Hope you have a beautiful day, and I'll catch you on the flip side.